On the morning of July 16, 1994, astronomers around the world pointed every available telescope at Jupiter and watched something that had never been witnessed in recorded human history: a comet named Shoemaker-Levy 9. Torn into 21 fragments by Jupiter's gravity the previous year, began slamming into the giant planet's atmosphere in a sequence of impacts that lasted 6 days. The largest fragment produced a fireball the size of the Earth. The dark scars left in Jupiter's cloud bands were visible for months afterwards with backyard telescopes. Every impact released energy equivalent to hundreds of millions of nuclear bombs detonating simultaneously, and Jupiter absorbed it all. It shrugged. Its atmosphere swallowed entire Earth-sized objects and left no permanent mark. That is what Jupiter is: an object of such mass, such gravitational dominance, such sheer physical scale, that the largest impacts we have ever witnessed in the solar system are, to it, nothing more than mild indigestion. And yet, for all its immensity, for all its awesome gravitational authority over the outer solar system, Jupiter failed at the one thing that would have made it the most consequential object in this corner of the galaxy. It failed to become a star. The question is, what would have happened if it had? If you enjoy videos that take the most dangerous hypothetical questions in planetary science and astrophysics, the ones that begin with "what if?" and end somewhere you never expected, and work through them with precision, care, and genuine physics rather than hand-waving spectacle, I'd genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about this topic is the one that almost every popular science article repeats: that Jupiter is almost a star, that it narrowly missed ignition, that it is a failed star sitting just below the threshold of nuclear fusion, and that with just a little more mess, it would have burst into flame. This is wrong in several important ways, and dismantling it carefully reveals something far more interesting than the misconception allows. Jupiter is not almost a star in the way that a glass of water is almost full. It is not a star in waiting, sitting at 95% of its fusion ignition threshold, needing only a small top-up to cross the line. Jupiter's current mass is approximately 1,000th the mass of the Sun, and the minimum mass required for hydrogen fusion, the threshold at which an object becomes a proper main sequence star, is approximately 80 times Jupiter's mass, or roughly 8% of the solar mass. Jupiter is not almost there. It is about 80 times too small. The threshold is not a hair's breadth away. It is nearly 2 orders of magnitude away. There is a genuine category of astronomical object, called a brown dwarf, which occupies the territory between the most massive giant planets and the least massive stars, and which does achieve some nuclear burning. Specifically, the fusion of deuterium, a heavy isotope of hydrogen, at masses above roughly 13 times Jupiter's mass. Jupiter, at 1 Jupiter mass, is not a brown dwarf either. It is simply a giant planet, the largest and most massive in our solar system, but unambiguously in the planetary category. The framing of Jupiter as almost a star persists because it makes for a tidy narrative of near-miss cosmic drama, but the physics does not support it. Jupiter is not close to the stellar threshold. It would need to gain roughly 79 additional Jupiter masses of hydrogen and helium, the equivalent of nearly 3 entire solar systems worth of planetary material, to even reach brown dwarf status. and another 67 Jupiter masses on top of that to ignite sustained hydrogen fusion and become a true star. So when we ask what if Jupiter became a star, we are not asking about a small perturbation of the current solar system. We are asking about a profound, catastrophic, civilization-ending restructuring of the entire solar neighborhood. We are asking what happens when an object that has spent 4.6 billion years as a giant planet suddenly, by whatever mechanism we choose to hand-wave into existence for the sake of the thought experiment, acquires 79 to 146 additional Jupiter masses of hydrogen and begins to fuse. The answer is extraordinary, and it begins, as almost all questions about stars do, with the physics of nuclear fire. Start with what a star actually is, and what has to happen inside Jupiter for the thought experiment to work. But first, let us understand what Jupiter actually is, in full physical detail, because the distance between Jupiter as it is and Jupiter as a star is not comprehensible without a clear picture of the starting point. Jupiter is the fifth planet from the Sun, and the largest object in the solar system after the Sun itself. Its mass is 1,898 kilograms, 318 times the mass of Earth, or about 1,000th the mass of the Sun. Its diameter at the equator is approximately 142,984 kilometers, making it roughly 11 times wider than Earth. If Earth were the size of a grape, Jupiter would be the size of a basketball. If you could hollow out Jupiter and pour Earths into it, you could fit about 1,300 of them inside. These numbers are large, but they still do not capture the essential character of Jupiter, which is that it is almost entirely gas. Jupiter has no solid surface in any meaningful sense. It is a ball of hydrogen and helium, with traces of water, ammonia, methane, and other compounds, that grows progressively denser and hotter as you descend from the visible cloud tops toward the center. At the cloud tops, the temperature is about 110 Kelvin, and the pressure is about 0.7 atmospheres, comparable to Earth's atmosphere at high altitude. Descend 150 kilometers, and the pressure reaches 22 atmospheres, and the temperature 430 Kelvin. Descend 1,000 kilometers, and you are at pressures of thousands of atmospheres and temperatures of thousands of Kelvin. Descend further into the deep interior, and the hydrogen, which is a gas at the surface and a liquid at intermediate depths, becomes something that has no counterpart in earthly chemistry: tematic hydrogen. Metallic hydrogen is a state of matter in which the pressure is so high, above about 1.4 million atmospheres, that the electrons are squeezed free of their parent hydrogen atoms and form a shared electron sea, the same configuration that makes metals like copper and aluminum electrically conductive. Metallic hydrogen conducts electricity, just as metals do. In Jupiter's interior, the layer of metallic hydrogen begins at roughly 20,000 to 50,000 kilometers below the cloud tops, roughly 1/3 of the way to the center, and extends inward, growing progressively denser. This metallic hydrogen layer is electrically conductive, and the circulation of this conducting fluid in Jupiter's deep interior, driven by the planet's heat flow and rotation, generates Jupiter's powerful magnetic field, the strongest planetary magnetic field in the solar system, roughly 10 to 20 times stronger than Earth's, extending far out into space and creating a magnetosphere that encompasses the Galilean moons and stretches millions of kilometers in all directions. At the very center of Jupiter, models predict a dense core of rocky and icy material, silicates, water, and iron, compressed to extraordinary densities by the weight of all the hydrogen and helium above it. The core mass is estimated at somewhere between 12 and 45 Earth masses, though there is significant uncertainty in this number because we cannot observe it directly. The Juno spacecraft, currently orbiting Jupiter, is measuring the planet's gravitational field with extraordinary precision to constrain the interior structure, and early Juno results suggest the core may be fuzzy, not a sharp boundary between the dense core and the surrounding hydrogen envelope, but a gradual transition region in which the heavy elements are mixed into the lower portion of the metallic hydrogen layer. This is a revision of earlier models that envisioned a sharp core boundary, and it changes our understanding of how Jupiter formed and how its interior has evolved over 4.6 billion years. Jupiter rotates remarkably fast for an object of its size. Its rotation period is 9 hours and 55 minutes, less than 10 hours, compared to Earth's 24 hours. This rapid rotation flattens Jupiter at the poles. Its polar diameter is about 9,000 kilometers smaller than its equatorial diameter, giving it a noticeably oblate shape, visible even through a modest backyard telescope. The rapid rotation also drives the planet's atmospheric circulation. The alternating bands of light and dark clouds, visible in Jupiter's atmosphere, the zones and belts, are the manifestation of this circulation. The zones are regions of rising gas, and the belts are regions of sinking gas, creating a system of eastward and westward jet streams that encircle the planet at different latitudes. These jet streams are extraordinarily stable. We have been observing them since telescopic astronomy began in the 17th century, and they have maintained roughly the same structure for hundreds of years. Embedded in this band structure are the giant storm systems that Jupiter is famous for, most notably the Great Red Spot, an anticyclonic storm roughly 16,000 kilometers across, larger than Earth, with winds reaching 432 kilometers per hour, that has been observed continuously since at least 1831 and may have existed for centuries before that. The Great Red Spot is the longest-lived storm in the known solar system, a planet-sized hurricane that has been churning without ceasing for longer than the United States has been a nation. Jupiter radiates about 1.7 times more energy than it receives from the Sun. This excess energy is the residual heat from its formation. Jupiter is still slowly contracting under its own gravity, releasing gravitational potential energy as heat, slowly cooling from the hot state in which it formed. The heat escaping from Jupiter's interior drives the large-scale atmospheric convection that powers the jet streams and the storm systems. In this sense, Jupiter is not purely passive. It is thermodynamically active, still releasing energy from its formation, still evolving, still losing heat to space. It will continue this slow contraction and cooling for billions of years to come. And Jupiter has moons, a system of at least 95 known moons, ranging from the 4 large Galilean satellites discovered by Galileo in 1610 to dozens of small, irregular captured bodies in highly eccentric outer orbits. The Galilean moons are worlds in their own right, each with its own geological history, interior structure, and surface conditions. Io, the innermost of the 4, is the most volcanically active body in the solar system. Its surface covered with hundreds of volcanic calderas and lava flows in shades of yellow, orange, and black from sulfur compounds. The source of Io's volcanic heat is tidal flexing, the gravitational squeezing and releasing of Io's interior by the combined tidal forces of Jupiter and the other Galilean moons, which are locked in a 1-2-4 orbital resonance that prevents their orbits from becoming circular and ensures that the tidal forces remain continuously at work. Io loses enormous amounts of sulfur dioxide gas to space through volcanic outgassing, and this material forms a torus of ionized gas around Jupiter's equator that is one of the most intense radiation environments in the solar system. Europa, the second Galilean moon, may be the most important object in the solar system for the question of life beyond Earth. Its surface is covered by water ice, crossed by long brown cracks that resemble the broken ice flows of Earth's polar seas. Beneath this icy shell, estimated to be 10 to 30 kilometers thick, models predict a global ocean of liquid water, kept liquid by the centidal heating that drives Io's volcanism, with an estimated total volume of water 2 to 3 times greater than all of Earth's oceans combined. If there is liquid water, and if there is geothermal heat from the tidal forces driving chemical reactions at the seafloor, then the conditions for life, the same conditions that sustain life at deep-sea hydrothermal vents on Earth, might exist in Europa's ocean right now. This is why the Europa Clipper mission, which launched in October 2024 and will arrive at Jupiter in 2030, is one of the most consequential planetary science missions of the current era. It will conduct detailed flybys of Europa, measuring the thickness of the ice shell, the salinity and chemistry of the ocean, the nature of the geology at the ice-ocean interface, and searching for plumes of water vapour that may be escaping from the ocean through cracks in the ice. Ganymede, the third Galilean moon, is the largest moon in the solar system, larger than Mercury, and is the only moon known to have its own internally generated magnetic field. Its interior is differentiated, with an iron core, a rocky mantle, and an ice shell, and models suggest it also harbours a subsurface ocean of salt water sandwiched between layers of ice at depth. The European Space Agency's JUICE mission, launched in 2023, will arrive at the Jupiter system in 2031 and ultimately enter orbit around Ganymede in 2034, making it the first spacecraft to orbit a moon other than Earth's. Callisto, the outermost of the Galilean moons, is the most heavily cratered surface in the solar system, a record of every impact it has sustained since the solar system formed, unchanged by geological activity. A pristine archive of the early solar system's bombardment history. Its surface is covered in billions of impact craters, ancient and sharp, eroded only by slow space weathering over 4.6 billion years. Callisto may also have a subsurface ocean, inferred from measurements of its response to Jupiter's magnetic field during Galileo's spacecraft flybys. All of this, the metallic hydrogen interior, the magnetic field, the Great Red Spot, the volcanic Io, the ocean-bearing Europa, the giant Ganymede, the ancient Callisto, would be profoundly altered or destroyed if Jupiter became a star. This is the context in which the transformation must be understood. Not just a planet becomes a star, in the abstract, but this specific extraordinary system, with its moons and their possible oceans, and their volcanic heat and their tidal dynamics, being replaced by something wholly different. Now we are ready to understand what a star actually is, and what has to happen inside Jupiter for the thought experiment to work. A star is, at its most fundamental, a gravitational contest. Gravity wants to collapse matter inward, toward a point of infinite density. The only thing that stops it is pressure, specifically, the pressure generated by the nuclear fusion reactions occurring at the star's core, which release energy in the form of photons, which push outward against the infall. A star is a negotiation between collapse and explosion, sustained across billions of years by the continuous burning of nuclear fuel. When the fuel runs out, the negotiation ends. Gravity wins. The star dies. For this negotiation to begin in the first place, the temperature at the core must reach approximately 10 million Kelvin, 10 million degrees. At this temperature, hydrogen nuclei, protons, are moving fast enough that when they collide, they can occasionally tunnel through the electromagnetic repulsion barrier that normally keeps positively charged particles apart, close enough that the strong nuclear force can bind them together. The fusion process converts hydrogen into helium through a series of steps called the proton-proton chain, releasing a small amount of energy, the difference in mass between the hydrogen inputs and the helium outputs, converted to energy by E equals mc squared. With each reaction, individual reactions release tiny amounts of energy. But a stellar core contains something like 10,577 hydrogen nuclei, and the reaction rate, integrated over the entire core, produces luminosities of 10 squared 6 watts or more. The Sun converts approximately 600 million tons of hydrogen into helium every second, releasing about 4 times 10 squared watts of power in the process, equivalent to detonating 91 billion megatons of TNT every second, sustained for 10 billion years. For Jupiter to join this club, its core would need to reach 10 million Kelvin. Jupiter's current core temperature is estimated at around 20,000 to 30,000 Kelvin, hot by any earthly standard, but less than 0.5% of what is needed for hydrogen fusion. The core pressure in Jupiter is estimated at around 40 to 70 megabars, tens of millions of times atmospheric pressure. This is impressive, but it is not sufficient. The core pressure needed to sustain hydrogen fusion in a star is on the order of tens of billions of atmospheres, hundreds of times higher than Jupiter's current core pressure. To bring Jupiter's core to stellar temperatures and pressures, you need to add mass. More mass means more gravitational pressure on the core, which means higher temperatures and densities. The relationship between core temperature and total mass in a self-gravitating ball of gas follows from the virial theorem, the same gravitational physics that governs how a gas cloud collapses to form a protostar. As you add mass to Jupiter, the core heats. As the core heats, the gas pressure increases, resisting further collapse, but also radiating energy away as heat. The object contracts. The contraction heats it further. This is exactly what happens during the formation of a protostellar object from a collapsing gas cloud, and it is what we are, in effect, proposing happens to a hypothetical inflated Jupiter. At around 13 Jupiter masses, if Jupiter were to somehow acquire 12 additional Jupiter masses of hydrogen, the core temperature reaches roughly 1 million Kelvin, hot enough to fuse deuterium. Deuterium fusion, unlike hydrogen fusion, does not require proton-proton tunneling. The deuterium nucleus, consisting of 1 proton and 1 neutron, fuses with a proton much more readily than proton-proton fusion, at lower temperatures and over a shorter timescale. The energy released by deuterium burning temporarily halts the gravitational contraction of the object, giving it a period of luminosity above what pure gravitational contraction would produce. This is the brown dwarf phase, objects between 13 and 80 Jupiter masses that burn deuterium but lack the mass for sustained hydrogen fusion. Deuterium burning, however, is short-lived. The supply of deuterium, which makes up only about 0.2% of all hydrogen, is exhausted in a few tens of millions of years, and the brown dwarf then slowly cools, growing dimmer over billions of years, eventually fading to a cold, dark, Jupiter-like object, but with far greater mass. At around 80 Jupiter masses, roughly 7.5% of the Sun's mass, or about 1/10 of a solar mass, the object reaches a mass where the core temperature can sustain hydrogen fusion on a long-term basis. This is the boundary between brown dwarfs and red dwarf stars, the lowest mass, coolest, longest-lived type of true star. A star of this mass would be an M-type red dwarf, with a surface temperature of roughly 2000 to 3000 Kelvin, a luminosity of perhaps 1/10,000th to 1,000th of the Sun's luminosity. A reddish-orange glow barely visible to the naked eye at interplanetary distances, and a lifespan of perhaps 1 trillion years, roughly 100 times longer than the current age of the universe. These are the most common stars in the galaxy. More than 70% of all stars are M-type red dwarfs, and they will continue burning long after every more massive star in the Milky Way has exhausted its fuel and gone cold. Now we have the physics. Jupiter, augmented to 80 times its current mass, becomes a red dwarf star. Our solar system becomes a binary star system, a configuration that, far from being exotic, is actually the most common stellar arrangement in the galaxy. More than half of all Sun-like stars are in binary or multiple star systems. The question is not whether such a configuration is possible. It obviously is, and we observe binary systems throughout the galaxy. The question is what it would mean for the solar system we actually live in, and for Earth and its biosphere, if Jupiter transformed into a red dwarf companion to a Sun. Before diving into the consequences, it is worth pausing to understand what binary star systems actually look like in practice, because the diversity of binary configurations is extraordinary, and the consequences for any planets within them depend strongly on which kind of binary we are discussing. The simplest binary systems are contact binaries, in which two stars are so close together that they share a common envelope of gas and are effectively touching. These are among the most dramatic objects in the stellar sky, with orbital periods of hours and tidal distortions that make each star into an elongated, egg-shaped body. The star W Ursae Majoris, one of the best-studied contact binaries, has two stars orbiting each other with a period of just 8 hours. No planet could survive in a stable orbit around such a system for any geologically significant period of time. The gravitational instabilities would eject any planet in the inner system within millions of years. Contact binaries are not promising abodes for life. At the other extreme are wide binary systems, in which two stars orbit each other at separations of hundreds to thousands of AU, separations so large that each star has plenty of room for its own planetary system, and the gravitational influence of the companion is barely a perturbation. Alpha Centauri, our nearest stellar neighbour, is actually a triple system. Alpha Centauri A and B orbit each other at a separation averaging about 24 AU, roughly the distance of Uranus from the Sun, with an orbital period of 80 years. This separation is wide enough that each of the two main stars could, in principle, host a stable planetary system in the inner few AU, though simulations suggest that planets in orbits crossing the habitable zones of both stars would be destabilized. Proxima Centauri, the third member of the system, orbits the Alpha Centauri pair at a distance of roughly 13,000 AU, so wide that its gravitational influence on potential planets around Alpha Centauri A or B is negligible. Proxima Centauri itself hosts at least one confirmed planet, Proxima Centauri b, in its habitable zone. Our hypothetical solar system with Jupiter star falls in between these extremes. Jupiter's current orbital distance of 5.2 AU from the Sun places Jupiter star close enough to the Sun to significantly influence the inner solar system, but far enough to potentially allow stable planetary orbits within a few AU. The separation of 5.2 AU is broadly comparable to the separations seen in binaries, like Gamma Cephei, a binary star system in which a planet has been confirmed orbiting the primary star at about 2 AU, despite the gravitational influence of a red dwarf companion at roughly 20 AU. Or Kepler-16, a circumbinary planet system in which a Saturn-sized planet orbits both members of a binary system from outside, completing an orbit roughly every 229 days. Or the TRAPPIST-1 system, which is a single M-dwarf with 7 planets, a reminder that even the most common, simplest type of star in the galaxy can host a remarkable planetary architecture. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized our understanding of planetary systems around binary stars. Kepler discovered dozens of circumbinary planets, planets orbiting both members of a binary system from outside, demonstrating that planets can form and persist in the dynamically complex environment of a binary system. These planets tend to orbit near or slightly outside the critical semi-major axis, the minimum orbital distance at which a circumbinary orbit is stable against gravitational perturbations from the binary pair. For a binary, like our hypothetical Sun plus Jupiter star, the critical semi-major axis for circumbinary orbits would be roughly 3 to 5 times the binary separation, about 15 to 25 AU, well outside Jupiter's current orbit. Earth, at 1 AU, is far too close to the binary center for a circumbinary orbit, and instead occupies a circumsolar orbit around the primary star, the Sun, inside the gravitational sphere of influence of the primary. Whether Earth's circumsolar orbit at 1 AU would be stable in the presence of Jupiter star at 5.2 AU depends on detailed numerical simulations, and the results vary depending on the specific orbital parameters. The general conclusion from such simulations is that planets in relatively circular orbits inside about 2 to 3 AU around a solar mass primary with a red dwarf companion at 5 AU or beyond can maintain stable orbits over giga-year timescales, though with significant variations in eccentricity and inclination. Earth's orbit would not be immediately destabilized, but it would be perturbed, the small but real gravitational tugs from Jupiter star, varying in direction and magnitude as Jupiter star moves in its orbit around the Sun, would cause Earth's orbit to evolve over millions and tens of millions of years in ways that the current solar system, with planetary Jupiter rather than stellar Jupiter star, does not experience. This orbital evolution matters for habitability. The Milankovitch cycles, the periodic variations in Earth's orbital eccentricity, axial tilt, and the precession of its orbit are driven by the gravitational interactions of the planets, primarily Jupiter and Saturn, on timescales of tens to hundreds of thousands of years. These cycles are responsible for the pacing of ice ages and interglacial periods throughout Earth's climate history. Their small perturbations, orbital eccentricity oscillating between 0 and 0.06, axial tilt varying between 20 and 24.5 degrees, but they are climatically significant. With Jupiter star instead of Jupiter, and with Jupiter star exerting 80 times more gravitational influence, the equivalent of the Milankovitch cycles would be far larger in amplitude and possibly different in period. The variations in Earth's orbital eccentricity could be much greater, potentially reaching values of 0.1 to 0.2 or more, which would drive much larger seasonal extremes and global temperature swings than the current ice age cycles. Whether these larger swings would make Earth less habitable depends on whether the planet remained within the habitable zone throughout the orbital variation, and whether the climate system's feedbacks, the carbon silicate cycle, the ice albedo feedback, the water vapor feedback, could buffer the larger swings without tipping into a runaway ice house or greenhouse state. Begin with the immediate physical consequences of the transformation. The moment Jupiter ignites as a star, the moment nuclear fusion begins in its core, and it begins radiating energy, rather than merely reflecting sunlight, the solar system changes irreversibly. A red dwarf of 80 Jupiter masses emits roughly 1/10,000th of the Sun's luminosity, about 4 times 10 squared watts, compared to the Sun's 3.8 times 10 squared, 6 watts. This is, in absolute terms, an enormous power output, roughly 100,000 times the total power consumption of human civilization. But compared to the Sun, it is tiny. The new star, let us call it Jupiter star, would be roughly 3.6 astronomical units from the Sun at Jupiter's current orbital location, or about 540 million kilometers away. But before considering what Jupiter star means for Earth, consider what it means for Jupiter's moons. The transformation of Jupiter into a star would be the most catastrophic event ever experienced by the Galilean satellites, and understanding their fate illuminates the physical severity of what we are discussing more vividly than any abstract calculation. Io, already the most volcanically active body in the solar system, receives its volcanic heat primarily from tidal flexing caused by the gravitational interactions with Jupiter and the other Galilean moons. As Jupiter transforms and its mass increases enormously, recall we are adding 79 Jupiter masses of material to reach the minimum stellar threshold. The tidal forces on Io during the mass addition phase would increase by similar factors. But this is secondary. What destroys Io is not the tidal forces from the increased mass. What destroys Io is the radiation from Jupiter star once emission occurs. A red dwarf of 80 Jupiter masses, at Io's distance of roughly 422,000 kilometers from Jupiter's center, provides an energy flux of approximately 2.8 times 10,007 watts per square meter. For comparison, the energy flux from the Sun at Earth's distance is 1,361 watts per square meter. Jupiter star, from Io's perspective, delivers roughly 20,000 times more energy per square meter than the Sun delivers to Earth. At this irradiation level, Io's surface temperature would reach thousands of Kelvin, far above the melting point of any silicate rock, far above the boiling point of sulfur dioxide. Io would be vaporized. Not heated to higher volcanic activity. Vaporized. The thin atmosphere of sulfur dioxide that currently exists around Io, sustained by volcanic outgassing, would be blasted away by the stellar wind from Jupiter's star within years of ignition, and the solid surface would begin to ablate, to be stripped away, atom by atom, by the intense radiation and particle bombardment over millions of years. Europa's fate is, if anything, more poignant, because it is not just a geological body being heated to destruction. It is potentially a world harbouring liquid water, and therefore possibly life, being sterilized. The ice shell covering Europa's ocean, approximately 10 to 30 kilometers thick at present, would begin melting almost immediately under the intense irradiation from Jupiter's star. The melting would proceed from the top down as the stellar radiation heats the ice surface faster than the tidal heat from below could compensate. The ice shell would thin, water vapor would begin escaping into space from the surface. The ocean, exposed to vacuum as the ice shell melts away, would begin to boil from the top, while remaining liquid or warm at depth, sustained by tidal heating for a period. But the tidal heating itself would change as Europa's orbital dynamics evolved in response to the transformed Jupiter. The 1 to 2 to 4 resonance among Io, Europa, and Ganymede that drives tidal heating might be disrupted by the mass increase and the changes to the orbital architecture. Over millions of years, Europa would lose its ocean. The water, dissociated by the intense ultraviolet radiation from Jupiter's star, would escape into space as hydrogen and oxygen. What remains would be a bare rock, stripped of its water, its ice, its atmosphere, baked in the radiation of its former parent planet, now a star. Ganymede and Callisto, at greater distances, would fare slightly better initially, but ultimately share the same fate as the inner moons. Ganymede, at 1.07 million kilometers from Jupiter, receives about 4.4 times 10 million watts per square meter from Jupiter *, roughly 3,200 times the solar flux at Earth. Its ice-rich surface would melt, its subsurface ocean would evaporate, its atmosphere would be stripped. Callisto, at 1.88 million kilometers, receives somewhat less, about 1.4 times 10 to the power of 6 watts per square meter. But even this is 1,000 times the solar flux, enough to drive the evaporation of all ice on its surface within millions of years. The entire Galilean moon system, this remarkable collection of worlds that has been the subject of so much scientific fascination and astrobiological speculation, would be sterilized and largely destroyed within tens of millions of years of Jupiter's ignition as a star. The smaller moons of Jupiter, the dozens of irregular captured objects in the outer part of the Jovian system, would fare differently depending on their distance and composition. The innermost small moons, orbiting within the Galilean moon system, would be vaporized quickly. The outermost irregular moons, orbiting at distances of tens of millions of kilometers, would receive far less radiation and might survive as bare rocky or metallic objects, their volatile components driven off, but their cores intact. They would become small, airless, radiation-baked rocks, orbiting Jupiter star in highly eccentric orbits, not moons of a planet, but minor bodies in eccentric orbits of a star. The asteroid belt, currently maintained in a roughly stable configuration by Jupiter's gravitational resonances, would be dramatically sculpted by the mass increase. Jupiter's current gravitational resonances with the asteroid belt, the Kirkwood gaps, named for the American astronomer Daniel Kirkwood, who identified them in 1866, are regions of the belt depleted of asteroids because orbital periods at those distances are simple fractions of Jupiter's orbital period. Objects in these resonances experience periodic gravitational kicks that pump up their orbital eccentricities until they are eventually ejected from the belt. With Jupiter at 80 times its current mass, these resonances would be dramatically stronger, and the clearing of material from resonant orbits would be far more effective. The asteroid belt, already depleted compared to the solid material that originally existed in that region, would be swept largely clean within a few 100 million years. Most of the belt material would be ejected either into the inner solar system, sending a prolonged bombardment of asteroids into Earth, Mars, and Venus, or into hyperbolic orbits that leave the solar system entirely. The belt would not disappear instantaneously. It would be steadily eroded, sending periodic swarms of debris into the inner solar system over hundreds of millions of years, as Jupiter star's resonances slowly clear the region. What would Earth experience as a result? The inner solar system bombardment from the cleared asteroid belt and perturbed outer solar system would be severe, perhaps comparable to the late heavy bombardment that Earth experienced about 3.9 billion years ago, when a reorganization of the outer planet orbits is thought to have destabilized a large reservoir of debris and sent a massive pulse of impactors into the inner solar system. The late heavy bombardment lasted perhaps 200 million years and left impact craters all over the Moon's surface, craters we can still see today. A Jupiter star-driven bombardment might be more intense and longer lasting, given the dramatically amplified gravitational influence of the new stellar companion. The frequency of large impacts on Earth, the kind that cause mass extinctions, would increase substantially during this period. What would this look like from Earth? The brightness of a star, as seen from a particular distance, depends on its luminosity and the inverse square of the distance. Jupiter star, with 1/10,000th of the Sun's luminosity and positioned at roughly 3.6 AU from Earth at closest approach, since Earth and Jupiter both orbit the Sun, would appear in Earth's sky with a magnitude of roughly 4 to 6 depending on its exact distance, comparable to the planet Venus at its brightest, or in some configurations slightly brighter. It would be easily visible in daylight and would cast faint shadows at night. It would not be blindingly bright. It would not turn night into day. It would be extraordinary, a second sun, small and ruddy, visible in the daytime sky, but not apocalyptic in the simple visual sense. But the visual brightness is the least important consequence. The radiative output of Jupiter's star, the energy it pours into the solar system, would be added to the Sun's existing output, and while the total additional power is small compared to the Sun, the geometry matters. The Sun illuminates the solar system from a fixed central point. Jupiter's star illuminates it from a different point, moving in its orbit around the Sun, sometimes on the same side of Earth as the Sun, and sometimes on the opposite side. When Jupiter's star is on the opposite side of Earth from the Sun, when Earth is between them, it illuminates Earth from behind at night. The night side of Earth receives additional radiation from Jupiter's star. The temperature contribution to Earth's surface from Jupiter's star at its peak would be tiny, perhaps raising the global average temperature by a fraction of a degree, an effect dwarfed by the Sun's influence. But the illuminated nights, the shadow-casting second sun, the complex patterns of light and shadow created by having two stellar bodies at different positions in the sky, these would transform the character of the human experience of sky and time in ways that go beyond pure temperature effects. Days, nights, and seasons would become vastly more complex. Currently, Earth has one sun, one day-night cycle, and seasons determined by its axial tilt relative to its orbital plane around that one sun. With a second star in the system, the illumination pattern of Earth's surface depends on the relative positions of both stars, both the Sun and Jupiter star, at every moment. There would be days when Jupiter star is above the horizon, while the Sun is below it, providing an eerie ruddy twilight for hours before and after the standard sunrise and sunset. There would be nights when Jupiter star is also below the horizon, giving true darkness. There would be rare alignments, when Earth, Jupiter star and the Sun are approximately collinear. That would produce either partial eclipses of the Sun if Jupiter star passes in front of it from Earth's perspective, which would not happen given the geometry, but the alignment would be notable, or enhanced illumination from both stars simultaneously. The orbital dynamics of a binary star system are determined by the masses and separation of the two stars and the positions of the planets within the system. A planet in a binary system can exist in two configurations: a circumbinary orbit, in which the planet orbits both stars together from a large enough distance that the binary system appears approximately as a single gravitational source, or a circumstellar orbit, in which the planet orbits one of the two stars in a close orbit, far enough inside the binary that the gravitational influence of the other star is a perturbation rather than a dominant force. Earth is currently 1 AU from the Sun. Jupiter is 5.2 AU from the Sun. If Jupiter becomes Jupiter's star, Earth is well within the circumstellar region. It orbits the Sun at a distance far inside its orbit of Jupiter's star, and the gravitational influence of Jupiter's star on Earth's orbit would be significant but not necessarily destabilizing. The gravitational effect of Jupiter's star on Earth's orbit depends on the mass. At 80 Jupiter masses, about 8% of the Sun's mass, Jupiter's star exerts a gravitational influence on Earth that is roughly 8% of the Sun's influence, modulated by the varying distance between Earth and Jupiter's star, as both orbit the Sun. This would cause Earth's orbit to precess, the orientation of the ellipse slowly rotating over time, and would produce periodic variations in Earth's orbital eccentricity and inclination. Whether these perturbations accumulate to the point of destabilizing Earth's orbit depends on the specific resonances involved and the detailed numerical simulations of the gravitational dynamics. The current solar system is already perturbed by Jupiter's gravity. Jupiter's gravitational influence is responsible for the existence of the asteroid belt. It prevented the material between Mars and Jupiter from accreting into a planet, and it regularly clears debris from its orbital resonances, clinging material into the inner solar system and occasionally toward Earth. Jupiter also acts as a gravitational shield, deflecting or capturing comets and asteroids that would otherwise penetrate the inner solar system. The Shoemaker-Levy 9 impact we opened with is a perfect illustration of this shield effect. A comet captured by Jupiter's gravity and ultimately destroyed by it, rather than continuing into the inner solar system where it might have threatened Earth. If Jupiter becomes Jupiter's star at 80 Jupiter masses, roughly 80 times more massive than it currently is, its gravitational influence on the inner solar system is correspondingly amplified. The asteroid belt, already sculpted by Jupiter's current gravity, would be dramatically disrupted. The orbital resonances that currently maintain the belt in a relatively stable configuration would be modified, and depending on the details of the mass increase and the resulting orbital evolution, a significant portion of the asteroid belt's material could be destabilized and flung into the inner solar system in an intense bombardment lasting millions of years. The effect on the outer solar system would be equally profound. Saturn, Uranus and Neptune, the other giant planets, all orbit at distances within Jupiter's current orbital domain or beyond it. If Jupiter's mass increases to 80 Jupiter masses, the gravitational dynamics among the outer planets would be radically altered. Saturn orbits at 9.5 AU from the Sun, compared to Jupiter's 5.2 AU. The gravitational interaction between an 80 Jupiter mass Jupiter star and Saturn would be vastly stronger than the current Jupiter-Saturday interaction, and depending on the orbital mechanics, Saturn's orbit could be significantly modified, either pushed to a more distant orbit, pulled to a closer one, or in extreme cases, ejected entirely from the solar system. Uranus and Neptune, at 19 and 30 AU respectively, would also experience enhanced perturbations. The entire orbital architecture of the outer solar system, which took hundreds of millions of years to settle into its current configuration, would need to rearrange itself around the new gravitational reality. This process would not be instantaneous or gentle. It would involve a period of chaotic gravitational interactions, close encounters between planets, ejections of some bodies from the system entirely, and a rain of comets and asteroids from destabilized reservoirs into the inner solar system that could last tens of millions of years. But let us set the chaos of orbital rearrangement aside, because even in the best-case scenario, where Jupiter ignites as a star and the inner solar system's orbits are only mildly perturbed, the effects on Earth are sufficiently dramatic to change the planet in ways that would be irreversible on human blow. Timescales. The first and most immediate effect is photobiological. All life on Earth has evolved in an environment lit by a single star, the Sun, with a specific spectral distribution, peaking in the visible and near-infrared. The Sun's light drives photosynthesis in plants and phytoplankton, provides the ultraviolet radiation that synthesizes vitamin D in animal skin, governs the circadian rhythms of every organism that has a biological clock, and shapes the behavior of animals that are either diurnal or nocturnal in response to the predictable day-night cycle. A second stellar body in the sky, even a dim one, disrupts the predictability of the light environment in ways that evolution has not prepared terrestrial life for. The circadian rhythm, the roughly 24-hour biological clock that governs sleep and wakefulness, hormone secretion, metabolic rate, and dozens of other physiological processes in virtually every animal, is entrained primarily by the cycle of light and darkness. When the light-dark cycle becomes unpredictable, when there are nights illuminated by Jupiter stars' ruddy glow, when there are prolonged periods of continuous low-level light, during the phases when both the Sun and Jupiter star are above the horizon simultaneously, the circadian clocks of organisms designed for a strict 24-hour light-dark cycle would be disrupted. In the short term, this would cause the equivalent of permanent jet lag for every organism on Earth. In the long term, over thousands of generations, evolution would adjust, selecting for organisms capable of functioning in the new light environment, but the adjustment would not be clean or free of cost. Species, unable to adapt, would be disadvantaged. Ecosystems dependent on the synchronized behavior of different species, predators that rely on prey being nocturnal, pollinators whose activity patterns are tightly tied to light cycles, would be disrupted in complex cascading ways. The effect on plant physiology will be equally significant. Photosynthesis in plants is not simply proportional to total light intensity. It depends on the spectral composition of the light and on the plant's ability to sense and respond to photoperiod, the length of the day relative to the night. Photoperiodism controls flowering time, leaf senescence, and dormancy in plants across the world. A second stellar body that produces significant light output during the night would confuse the photoperiodic cues that plants use to time their life cycles. Flowering times would be disrupted, seed set could be affected, and the synchronization of plant life cycles with seasonal temperature changes, which itself depends on photoperiod as an anticipatory signal, could be broken. This is not a catastrophic extinction scenario in the immediate term. Plants are adaptable and have evolved in environments with highly variable light regimes during geological history. But it is a significant perturbation to the biological machinery of the biosphere. Now, let us consider the thermal effects, because they are more calculable and in some ways more dramatic than the biological ones. Jupiter star, at 80 Jupiter masses, has a luminosity of roughly 10 to the power of 4 solar luminosities. The effective surface temperature of such a red dwarf is approximately 2,500 Kelvin, well below the Sun's 5,778 Kelvin surface temperature. The light it emits is heavily weighted toward the red and near-infrared, with very little blue or ultraviolet output. The total power received at Earth's surface from Jupiter's star depends on its distance, which varies over the course of its orbit around the Sun. At Jupiter's current orbital distance of 5.2 AU from the Sun, Earth's distance from Jupiter ranges from 4.2 AU when Earth and Jupiter are in opposition, Jupiter is opposite the Sun in Earth's sky, to 6.2 AU when Earth and Jupiter are in conjunction, Jupiter is on the far side of the Sun. The energy flux at Earth from Jupiter's star at its nearest point is approximately 10⁻⁴ solar luminosities divided by 4.2 AU squared in solar units, giving roughly 5.7 times 10⁻⁶ of the solar energy flux at Earth. The Sun provides about 1,361 watts per square meter at Earth's distance. Jupiter's star provides roughly 0.08 watts per square meter at closest approach. For comparison, the full moon provides about 0.01 watts per square meter. Jupiter's star would be roughly 8 times brighter than the full moon. Spectacular to look at, easily visible in daylight, but thermally negligible. The contribution to Earth's mean temperature would be a fraction of a degree Celsius, less than the effect of a modest volcanic eruption, far less than current anthropogenic warming. This, however, changes dramatically if Jupiter were substantially more massive than the minimum stellar threshold. If we ask what if Jupiter became a Sun-like star, a G-type main sequence star with the Sun's luminosity and surface temperature, we need Jupiter to acquire approximately 1,000 Jupiter masses, or about one full solar mass. Two objects of equal mass, the Sun and a second Sun, in a binary configuration at 5.2 AU separation, would create a solar system with dynamics unlike anything we have discussed so far. The gravitational center of the binary, the barycenter, would be exactly midway between them, at 2.6 AU from each. Earth's current orbit at 1 AU from the Sun would place it well inside the circumsolar orbit of the primary star, and the gravitational influence of the second star would cause Earth's orbit to evolve rapidly. Numerical simulations of binary star systems with separations of around 5 AU consistently show that planets in inner orbits around one of the stars experience significant perturbations that can either circularize or destabilize their orbits. Timescales of millions to tens of millions of years, depending on the mass ratio and the specific orbital parameters. But the more immediate effect of a second solar mass star at 5.2 AU from the Sun would be thermal. A star of the Sun's luminosity at 4.2 AU from Earth, the closest approach provides roughly 5.7 times 10⁻² solar luminosities. At Earth, roughly 5.7% of the Sun's energy. The total energy input to Earth's surface would increase by roughly 6%. This sounds modest, but is, in climate terms, catastrophic. The current difference in solar energy input between an ice age and an interglacial period, between the depths of glaciation and the warm Holocene we live in, is less than 1%. An increase of 6% in total solar input would raise Earth's equilibrium temperature by approximately 10 to 15 degrees Celsius, depending on feedback mechanisms. This would eliminate virtually all permanent ice, flood coastal areas to depths of tens of meters from complete ice sheet melting, fundamentally alter global atmospheric circulation patterns, and create a biosphere entirely unlike anything that has existed in the last hundreds of millions of years of Earth's history. It would not kill all life, life is remarkably resilient, but it would end the world as we know it. And this is at maximum separation, when the second star is as close as it can get in orbit. When it is on the far side of the Sun at 6.2 AU, the additional energy input is roughly 3.3%. The seasonal variation in energy input from the second star as it orbits the Sun over its roughly 11.86-year period, matching Jupiter's current orbital period, would drive temperature cycles on Earth with a period of about 6 years, as Earth moves from closest to farthest approach to the second star over the first half of its orbit and back again. These cycles, superimposed on Earth's own annual seasonal cycle, would create an unprecedentedly complex seasonal pattern. Not 2 seasons per year, but a complex interference pattern of seasonal variation driven by 2 different orbital periods with 2 different amplitudes. Let us now push the thought experiment to its most dramatic form. Forget about minimum stellar mass. Forget about modest red dwarfs. Ask, what if Jupiter became something genuinely massive, say 10 times the Sun's mass? A blue-white O-type or B-type star, of the kind that blazes for only tens of millions of years before exploding as a supernova. This is obviously far beyond what any plausible mechanism would do to Jupiter, but it is instructive because it illuminates the extreme end of the possibility space and reveals the physics at its most unambiguous. A star 10 times the Sun's mass has a luminosity of roughly 10,000 times the Sun, not because of a simple linear scaling, but because stellar luminosity scales approximately as the 4th power of mass for massive stars. A star twice as massive as the Sun is about 16 times more luminous. A star 10 times as massive is about 10,000 times more luminous. At Jupiter's distance of 5.2 AU from the Sun, a 10,000 solar luminosity star would provide approximately 370 times the energy flux to Earth that the Sun currently does. Earth's equilibrium temperature would rise by a factor of 370 to the 25th power, the 4th root of 370, because luminosity scales as temperature to the 4th power, approximately a factor of 4.4. Earth's current mean temperature is about 288 Kelvin. Multiplying by 4.4 gives approximately 1267 Kelvin, hot enough to melt lead, hot enough to vaporize carbonates and sulfates from the rock, hot enough to drive most of the water from the surface into the atmosphere as steam, before eventually stripping it from the planet through atmospheric escape. Earth, under such conditions, would not be remotely habitable. It would more closely resemble Venus, a world of runaway greenhouse effect and crushing atmospheric pressure, except hotter. Much hotter. The oceans would boil, the rocks would begin to soften, the atmosphere would be a mix of steam and outgassed volcanic volatiles, and thousands of atmospheres of pressure. In a few million years, the intense ultraviolet radiation and particle winds from the massive star would strip the atmosphere entirely, leaving a bare, scorched rock resembling Mercury, but at a temperature that would make Mercury look temperate. But the trajectory of a massive B-type or O-type star is not merely one of relentless irradiation. Massive stars evolve dramatically during their lifetimes, and the evolution of Jupiter's star through its stellar life would subject the solar system to a sequence of increasingly extreme conditions. In the first few million years, the main sequence phase, Jupiter's star burns hydrogen in its core with a ferocity proportional to its mass. A 10 solar mass star burns through its hydrogen fuel roughly 1,000 times faster than the Sun does, living on the main sequence for only about 10 million years, rather than the Sun's 10 billion. During this phase, its luminosity is roughly 10,000 times the Sun's. Its surface temperature is about 20,000 Kelvin, and its light is weighted heavily toward the ultraviolet. The ultraviolet flux from Jupiter's star would strip Earth's ozone layer, the shield of ozone molecules in Earth's stratosphere that currently absorbs most of the sun's harmful ultraviolet radiation, within years of the star's ignition, exposing the surface to intense UV bombardment. Without an ozone layer, even the reduced UV fraction that passed through the remaining atmosphere would be lethal to most surface life, including all photosynthetic organisms. Marine life, protected by even a few meters of ocean water from the UV, would survive longer, but the warming of the oceans from the increased total radiation would drive stratification, reducing the circulation of nutrients from deep to shallow water and starving the phytoplankton that form the base of the marine food web. As Jupiter's star exhausts its hydrogen and evolves off the main sequence, swelling into a supergiant, increasing its luminosity further, cooling slightly on the surface, but increasing in size enormously, the configuration of the solar system changes again. A 10 solar mass star in the red supergiant phase can reach a radius of several hundred solar radii, hundreds of times the Sun's current size. At Jupiter's orbital distance of 5.2 AU, a star with a radius of 300 solar radii would have a radius of about 1.4 AU, meaning its photosphere would extend to within the orbit of Earth. Earth would be inside the expanding star, not near it. Inside it. The tenuous outer envelope of the supergiant, while not dense enough to burn Earth, like the core, would create enormous aerodynamic drag on Earth's orbit, causing Earth to spiral inward through the stellar envelope. The outcome for Earth, its final infall into the denser inner layers, its disintegration in the ascending density of the stellar interior, would be a literal destruction. Earth consumed by the star that was once the largest planet in its solar system. And then, in tens of millions of years, a blink in geological time, a span shorter than the age of the dinosaurs, the massive star would exhaust its nuclear fuel through the complete sequence of fusion stages: hydrogen to helium, helium to carbon, carbon to oxygen and neon, oxygen to silicon, silicon to iron. Each stage is faster than the last. Helium burning lasts about 1 million years, carbon burning about 1,000 years, silicon burning about a day. The iron core, as we discussed in our treatment of neutron stars, cannot release energy through further fusion, and when it reaches the Chandrasekhar mass, it collapses in less than a second, triggering a core collapse supernova. The explosion would release approximately 10,444 joules of energy, with a peak luminosity comparable to the entire Milky Way galaxy for a few weeks. At Jupiter's distance of 5.2 AU, though by this point Earth has either been consumed by the expanding supergiant or has been ejected from the system by the mass loss from the wind-shedding late-phase star, the energy flux from the supernova would be extreme. If Earth somehow survived to the moment of the explosion, the supernova would expose it to a gamma-ray and X-ray flux sufficient to destroy any remaining atmosphere and sterilize the surface to bedrock in a matter of hours. The optical flash would be briefly brighter than the Sun, not by a small amount, but by many orders of magnitude. For a few weeks, Jupiter's star supernova would outshine the Sun by thousands to millions of times as seen from Earth. Then it would fade, leaving either a neutron star or a black hole at the center of an expanding nebula of stellar material racing outward at thousands of kilometers per second. The shockwave of expanding stellar material, the supernova remnant, would reach Jupiter's former orbital distance in years to decades, moving at roughly 10,000 kilometers per second. The inner solar system would be swept by ionized gas, travelling at 10% of the speed of light, delivering a pulse of kinetic and radiation energy that would ablate the surfaces of the surviving planets. Mercury, Venus, and any surviving fragments of Earth would be scoured. The solar system, after the supernova, would consist of the Sun, possibly slightly modified by the deposition of supernova ejecta, and a collection of battered, scorched, stripped planetary remnants orbiting in the glow of the cooling supernova nebula. Over thousands of years, the nebula would expand and cool, becoming a supernova remnant detectable across the galaxy, similar to the Crab Nebula, the remnant of the 1005C supernova observed by Chinese and Arab astronomers, whose central pulsar still powers a glowing web of ionized gas 6,500 light-years away. At the center of the nebula would be what Jupiter star had become, a neutron star, the extraordinary object of compressed nuclear matter that we discussed in full detail in a previous episode. With a mass between 1 and 2 solar masses compressed into a sphere 20 kilometers across, spinning hundreds of times per second, blazing in X-rays, pulsar beams sweeping through the remnant of what was once our solar system. This is the ultimate transformation of Jupiter, from a gas giant with magnificent moons to a pulsar in a supernova remnant. It is not a scenario we need to worry about in any practical sense. The physics prevents Jupiter from ever acquiring anywhere near this much mass. But it illustrates, with full physical clarity, what a star actually is and what the difference between planet and star means at the most fundamental level. The difference is not gradual. It is not merely quantitative. It is a categorical boundary between objects that radiate their own light through nuclear fire and objects that do not, between objects that explode as supernovae and scatter heavy elements across the galaxy, and objects that accumulate those elements, cool them, form planets from them, and provide stable orbits for those planets to circle for billions of years. Jupiter is on one side of that boundary. Everything that makes it Jupiter, its moons, its storms, its magnetic field, its complex interior, its role as a shepherd and shield for the inner solar system, exists because it is on that side of the boundary. The thought experiment of crossing the boundary reveals, by contrast, what we would lose if it had been crossed. And what we would lose is everything. Here is the deeper question, embedded in what if Jupiter became a star? Why didn't it? Jupiter is primarily composed of hydrogen and helium, the same raw materials that stars are made of. The solar system formed from a collapsing cloud of gas and dust approximately 4.6 billion years ago. And in that process, the vast majority of the material, some 99.86% of the total mass, was accreted by the Sun. The remaining 0.14% formed the planets, with Jupiter claiming the lion's share of that remainder, roughly twice the mass of all the other planets combined. Jupiter, in a sense, could have been a star. There was hydrogen and helium available. The process of gravitational accretion was the same process that built the Sun. What determined that Jupiter ended up as a planet rather than a star? The answer is a combination of mass and timing. The Sun formed first, collapsing from the densest region of the protostellar cloud, accreting the majority of the available material and igniting. When the Sun ignited, the intense radiation and particle wind it produced, the T-Tauri phase of young stellar evolution, in which a newly ignited star emits powerful winds and radiation that blast the surrounding protoplanetary disk, cleared the disk of remaining gas and dust within a few million years. By the time Jupiter had accreted to its current mass, the supply of additional gas was being rapidly depleted by the Sun's radiation. Jupiter grew as large as it did because it formed at the right distance from the Sun, far enough from the snow line the boundary beyond which water and other volatiles freeze, that it had access to the solid icy planetesimals that provided the seed core for runaway gas accretion, but close enough to the Sun that there was still plenty of gas available when that core was assembled. If Jupiter had formed earlier, or at a different location, or in a more massive protoplanetary disk, it might have accreted more mass and eventually reached stellar ignition. That it did not is a contingent fact of the solar system's formation history, of where the mass happened to be distributed and how fast it happened to accrete. Now consider what the biological history of Earth would look like in a solar system with Jupiter star, even in the best case minimum mass red dwarf scenario, where Earth's orbit remains broadly stable. Life on Earth has persisted for approximately 3.8 billion years, through extraordinary challenges, multiple global glaciations, snowball Earth events, mass extinctions, large asteroid impacts, volcanic eruptions that alter the atmosphere for millions of years, and the slow brightening of the Sun, which is about 30% more luminous today than it was when life first arose. A change that life's influence on the carbon cycle has managed to compensate through the gradual drawdown of atmospheric carbon dioxide. This resilience is remarkable, and it raises the question, could life have persisted on Earth through the additional stresses of a red dwarf companion? The carbon silicate cycle, the long-term geological thermostat that has regulated Earth's temperature over billions of years, works by removing carbon dioxide from the atmosphere through weathering of silicate rocks and re-injecting it through volcanic outgassing. When Earth cools, weathering slows, volcanic outgassing accumulates CO2, and the greenhouse effect warms the planet back up. When Earth warms, weathering accelerates, more CO2 is removed, and the planet cools. This negative feedback loop has kept Earth in the habitable zone despite the Sun's increasing luminosity for nearly 4 billion years. In a binary solar system, with Jupiter star introducing periodic variations in Earth's energy input over an 11.86-year orbital period, the carbon silicate cycle would still operate, but it would need to buffer a more complex input signal, one that varied not just on the slow multi-billion-year timescale of solar brightening, but also on the 11.86-year period of Jupiter star's orbit, and on whatever longer period cycles arose from the precession and eccentricity variations we discussed. Whether the carbon silicate cycle could buffer these variations depends on its response time, typically hundreds of thousands to millions of years, and the amplitude of the variation. For a minimum mass red dwarf Jupiter star, the additional energy input is so small, 0.1% of the Sun's output, that the carbon silicate cycle would barely register it. For a more massive red dwarf, or for the G-type companion scenario, the variations would be much larger and the buffering challenge correspondingly greater. Life would also face the challenge of adapting to a fundamentally different light environment, not just in terms of intensity, but in terms of spectrum. If these genes and follies are inherently damaged, and plants that power by 4, the wavelengths emitted to absorb red and blue, with maximum absorption at about 680 nanometers red and 430 nanometers blue, in the far red and near infrared, are not well absorbed by these chlorophylls. However, evolution is not limited to the chlorophylls that currently dominate Earth's biosphere. Other photosynthetic pigments exist. Bacteriochlorophylls, used by certain bacteria in anaerobic environments, absorb at 800 to 1000 nanometers, precisely the wavelengths that Jupiter star would emit most strongly. In a solar system with Jupiter star from the beginning, if life had evolved in this environment from the start, the photosynthetic organisms that dominated the biosphere might be tuned to Jupiter's star's spectrum, rather, or in addition to, the Sun's. A biosphere evolved in this environment might be richer in photosynthetic diversity, exploiting light from two different stellar sources with two different spectrum, rather than the single spectrum environment we currently inhabit. This line of thinking connects to a broader question in astrobiology about the spectra of red dwarf stars and the possibility of photosynthesis on their planets. Planets in the habitable zones of red dwarfs receive less total visible light than Earth does from the Sun, but they receive more near-infrared. Models of photosynthesis in these environments suggest that organisms tuned to harvest near-infrared photons would need to absorb more of them per photosynthetic reaction, potentially requiring different biochemistry, but not violating any physical principles. Some models predict that photosynthetic organisms on red dwarf planets might have dark or black coloration to maximize absorption across the limited spectrum available, rather than the green coloration of Earth's plants, which reflect green light. As a byproduct of having chlorophylls tuned to red and blue, a world illuminated primarily by a red dwarf might have dark red or black vegetation, a rust-coloured biosphere, absorbing the abundant near-infrared and the limited visible light with maximum efficiency. In our solar system with Jupiter star, this would not produce a dark vegetation Earth. The Sun would still dominate the total energy budget by a factor of roughly 10,000, but organisms in the orbital shadow of Jupiter star, in regions where Jupiter star's light was temporarily the dominant source. No such regions exist in our thought experiment, but the principle applies. Might evolve specialized photosynthetic pigments to harvest the unusual spectrum. Over billions of years of evolution in the binary solar system, the biosphere might develop a greater diversity of photosynthetic strategies, occupying niches created by the second star's different spectral output. None of this changes the fundamental conclusion. Jupiter is a planet. It did not become a star. The solar system we inhabit, with its single star and its giant planet guardian, and its collection of rocky inner worlds and its ocean-bearing moons, is what it is because of a specific sequence of formation events that happen to produce this particular configuration. The thought experiment of making Jupiter a star is valuable not because it is possible, or because it nearly happened, or because we need to worry about it. It is valuable because it illuminates, by contrast, what we have. It shows us, by asking what we would have lost, what the value is of what we have instead. In binary and multiple star systems throughout the galaxy, we see the full range of outcomes that were possible for our solar system. Some systems have two stars of nearly equal mass. Some have a dominant star and a much dimmer companion. Some have stars separated by only a few stellar diameters, so close that their surfaces nearly touch and material is transferred from one to the other. Some have companions separated by hundreds of AU, so distant that their gravitational interaction is weak enough for each to host its own planetary system. The solar system, with its single star and complement of planets, is not the most common outcome of stellar formation. Binary systems are more common than single stars, but it is far from rare. Roughly half of all Sun-like stars are single stars, without companions. We happen to live around one of them. If Jupiter had been born as a star, if the solar system had formed as a binary system with a small red dwarf companion at roughly Jupiter's current orbital distance, what would that have meant for the history of Earth? The question is genuinely uncertain and depends on the details of orbital dynamics, but several conclusions are defensible. But before pursuing those conclusions, It is worth spending some time on the story of how Jupiter came to be what it is, because that story reveals how contingent the entire solar system's architecture is. How close to a different configuration things might have been, and why the question, what if Jupiter became a star, is not merely a fantasy, but a question about the actual possibilities that existed during the solar system's formation. The solar system formed approximately 4.6 billion years ago from a rotating disk of gas and dust, the solar nebula, left over after the Sun coalesced from the densest part of a collapsing molecular cloud. The disk had a total mass of perhaps a few percent of the Sun's mass, and it extended from near the Sun's surface out to hundreds of AU. Within this disk, small solid particles stuck together by electrostatic forces and van der Waals interactions, growing from dust grains to pebbles, to boulders, to planetesimals, rocky and icy bodies ranging from meters to kilometers in size. These planetesimals collided and merged, building up the terrestrial planets and the cores of the giant planets over millions to tens of millions of years. Jupiter's formation is thought to have begun with the assembly of a solid core, a roughly 10 to 20 Earth mass object composed of silicates and ices that formed beyond the snow line, the distance from the Sun, where water and other volatiles condense from gas into ice, roughly 2.7 AU. In the early solar system, beyond the snow line, solid material was more abundant because water ice contributed significantly to the mass budget. Jupiter's core, assembling at 5 AU, where there was both abundant solid material and still a substantial reservoir of gas in the disk, reached a critical mass, about 10 Earth masses, at which point it began a runaway accretion of gas from the surrounding disk. Gas poured onto the growing protoplanet, and within perhaps 1 million years, Jupiter reached something close to its current mass, sweeping up the surrounding gas until the gas was either consumed or blown away by the Sun's increasing luminosity during its T-Tauri phase. The timing was everything. Had Jupiter's core assembled faster, perhaps because the local density of solid material was higher, or because the growth of planetesimals was more efficient, it might have grown to its critical mass earlier, when there was more gas available in the disk, and accreted a larger total mass. Models of giant planet formation show that small variations in the formation efficiency can produce objects ranging from 1 to 10 Jupiter masses, or more, from similar starting conditions. Had Jupiter accreted 5 or 10 times more gas, had conditions been slightly different in the early solar disk, it might have reached 10 to 13 Jupiter masses and become a super-Jupiter or low-mass brown dwarf, permanently just below the deuterium burning threshold. Had it accreted 80 Jupiter masses, it would have become a red dwarf, and our solar system would have had 2 suns from the very beginning. The formation of Jupiter's mass also had consequences for the rest of the solar system that are still being untangled. The Grand Tack hypothesis, a model of early solar system dynamics developed by Kevin Walsh and collaborators in the 2004s, proposes that Jupiter initially formed at about 3.5 AU, then migrated inward toward the Sun to about 1.5 AU as it interacted with the gas disk, sweeping up and scattering the solid material in the inner solar system, reducing the mass available to form Mars, which ended up unusually small for an inner planet, and then migrating back outward to its current position as it was pushed by the gravitational influence of the growing Saturn. The inward then outward migration of Jupiter, the tack complex says, explains several otherwise puzzling features of the solar system, including the small mass of Mars, the composition and orbital distribution of the asteroid belt, and the delivery of water and carbon to the early Earth from outer solar system sources. If Jupiter had been more massive, if it had been, say, 13 Jupiter masses, a brown dwarf, its interaction with the solar disk would have been more powerful. The gap it carved in the disk would have been wider and deeper. Its migration would have proceeded differently, and its encounter with the inner solar system would have been more violent. The terrestrial planets, Mercury, Venus, Earth, Mars, are the survivors of an early solar system that was sculpted by Jupiter's migration. With a more massive Jovian body, that sculpting might have swept the inner solar system more thoroughly, leaving fewer terrestrial planets, or planets in different orbits. The existence of Earth, with its specific mass and orbital radius and water content, all of which emerge from the specific early history of accretion and bombardment and migration in our solar system, is not independent of Jupiter's mass. Change Jupiter, and you change Earth, potentially beyond recognition. I suppose that you cannot see how much can also be a radical or complex scientific problem. This deep interdependence of solar system architecture is one of the most important insights of the last 3 decades of planetary science. The solar system is not a collection of independent objects that happen to end up in the same neighborhood. It is the product of 4.6 billion years of gravitational, collisional, and dynamical interaction among all of its parts, from the smallest asteroid to the largest planet. Every object's current orbit is the outcome of the entire history of gravitational interactions with every other object. Change one piece, make Jupiter twice as massive, or 3 times, or 80 times, and the entire system reconfigures. Not gradually, not merely quantitatively, structurally, qualitatively. Some configurations lead to stable inner solar systems with habitable planets. Some lead to the ejection of all inner planets. Some lead to the merger of planets and the radical simplification of the system. The solar system we have is one outcome of a stochastic, history-dependent process that could have produced very different results with only modestly different initial conditions. First, the stability of Earth's orbit would be reduced, though not necessarily eliminated. Computer simulations of binary star systems with separations of several AU and mass ratios similar to a Sun plus red dwarf binary consistently find that planetary orbits within the circumsolar zone can persist for billions of years, but with significantly larger variations in eccentricity and inclination than in the current solar system. Earth's orbit, perturbed by a red dwarf companion at Jupiter's distance, would oscillate between a more circular and a more elliptical configuration over cycles of millions of years. This would drive climate variations on Earth, ice ages and warm periods, of greater amplitude than those driven by the current Milankovitch cycles, which involve only small periodic variations in Earth's orbital parameters due to the gravitational tugs of Jupiter and the other planets. Second, the additional radiation from Jupiter's star, small but not zero, amounting to a few hundredths of a percent of the Sun's output, would provide a mild but continuous second illumination that would have subtly different spectral properties than the Sun. Red dwarfs emit almost no ultraviolet light. Their surface temperatures are too low to produce significant UV flux. The Sun's ultraviolet output is biologically significant in several ways. It drives the formation of the ozone layer by photodissociating molecular oxygen. It is responsible for vitamin D synthesis in vertebrate skin. And it may have been important in the prebiotic chemistry that produced the first organic molecules in the early Earth. The presence of a UV-poor second star in the sky would not subtract the Sun's UV, but it would add a new class of illumination, red-weighted light, that might have influenced the evolution of vision in early animals, the chemistry of the atmosphere, or the distribution of photosynthetically active organisms in ways we cannot fully predict. Third, and perhaps most consequentially for the history of life, the gravitational shield effect of Jupiter, the protection it provides to the inner solar system from cometary impacts by deflecting or capturing objects from the outer solar system, would be transformed. Jupiter currently occupies a specific gravitational position in the solar system that makes it an effective shield. At 80 Jupiter masses, Jupiter star's gravitational reach would be enormously amplified, extending its zone of influence deep into the Oort cloud, the vast spherical reservoir of comets at the outer edge of the solar system, extending to perhaps 100,000 AU from the Sun. The perturbations of this massively amplified gravity on the Oort cloud could drive a dramatic increase in the rate of cometary deflection toward the inner solar system, potentially causing an extended bombardment of the inner planets, far exceeding the late heavy bombardment that occurred 3.9 billion years ago. Alternatively, the massive companion could clear the Oort cloud more completely, reducing the long-term cometary flux to the inner solar system to levels below even the current rate. The direction of this effect, whether it means more impacts or fewer, depends sensitively on the orbital dynamics and is not easy to predict without detailed numerical simulations. But here is where the thought experiment opens onto the widest vista, the question that extends beyond the solar system and into the broader question of planetary habitability throughout the galaxy. Does having Jupiter as a gas giant planet, rather than a stellar companion, make Earth more or less habitable? This is known as the Jupiter as shield hypothesis, and it has been extensively discussed in the astrobiology literature since the 1990s, when cosmologist Michael Hart and astronomer Grems Weatherall proposed that Jupiter's gravitational shield role might be essential for the long-term habitability of Earth-like planets, and that solar systems without a Jupiter-equivalent giant planet in the outer system might be inhospitable to complex life. Weatherall's simulations suggested that without Jupiter, the rate of comet and asteroid impacts on Earth would be hundreds of times higher than it currently is, and that the frequency of mass extinction events would be correspondingly higher, potentially preventing the accumulation of the biological complexity needed for the evolution of animal life. This argument was influential and contributed to the broader hypothesis of a rare Earth. The idea that complex life requires not just a habitable zone orbit and liquid water, but a specific suite of planetary and stellar properties that may be uncommon in the galaxy: a large moon to stabilise Earth's axial tilt, a sun-like star, not too hot or too cold, a position in the galactic disk, not too close to dangerous stellar nurseries or the galactic centre, and a Jupiter-equivalent planet in the outer system to shield the inner planets from excessive bombardment. More recent research has complicated this picture. Simulations by Kevin Grazier and others found that Jupiter's gravitational influence is not simply protective, it is complex. Jupiter deflects some objects away from Earth, but it also perturbs others into Earth-crossing orbits that would not otherwise intersect Earth. The asteroid belt, sculpted by Jupiter's resonances, is both maintained in a stable configuration and periodically destabilized, sending occasional showers of asteroids into the inner solar system. The current rate of asteroid and comet impacts on Earth may be neither minimized nor maximized by Jupiter's presence. It may be somewhere in the middle, with Jupiter's net effect on the bombardment rate being modest rather than dramatic. The rare Earth hypothesis has been critiqued on multiple grounds, and the Jupiter is shield component is one of the less robustly supported elements of it. What the discussion reveals is that the question, what if Jupiter became a star, is not just an exercise in solar system dynamics. It is a question about what makes a planetary system habitable, what gravitational and radiative environment is conducive to the origin and sustained evolution of complex life. And it connects to the deepest questions in astrobiology about how common or rare Earth-like biospheres are in the galaxy. If binary star systems with red dwarf companions at 5 AU can support stable, habitable inner planets, and the evidence suggests that many can, then a version of our solar system with Jupiter star rather than Jupiter might still have produced a habitable Earth with some modifications to the biological history. If the gravitational perturbations from Jupiter star were strong enough to consistently destabilize Earth's orbit or drive excessive impact rates, then the answer is more pessimistic. There is one more aspect of the thought experiment that deserves attention, and it is the most intimate one. If Jupiter ignited as a star, if the night sky suddenly contained a second luminous body, visible in daylight, casting shadows at night, what would it mean for the humans living through it? The history of human culture has been shaped, in ways too deep to fully enumerate, by the sky. The sun has defined time, the day, the year, the calendar, for every civilization that has ever existed. The night sky, with its stars and moon and occasional bright planets, has been the template on which mythology, religion, navigation, and the first stirrings of scientific inquiry were written. The Milky Way overhead has inspired wonder in every culture that has looked up at it. In this context, the sudden appearance of a second star in the sky, even a dim one, even one that is obviously different from the sun, would be among the most transformative events in human cultural history. Consider the effect on timekeeping alone. Human calendars are built around the sun. The year is defined by Earth's orbit around the sun. The day is defined by Earth's rotation relative to the sun. The seasons are defined by the relationship between Earth's axial tilt and its orbital position around the sun. If a second star enters the solar system, it introduces a new orbital period, currently 11.86 years for Jupiter, but potentially altered by the mass change. That would quickly become culturally significant. Agricultural civilizations would need to understand and account for the roughly 12-year cycle of Jupiter's star's position in Earth's sky, when it is near the Sun conjunction and when it is opposite the Sun opposition. Because the variations in the Sun, illumination and possibly temperature it causes over this cycle would affect growing seasons, nighttime temperatures, and the general character of each year within the cycle. The 12-year cycle would almost certainly become embedded in calendrical systems, in astrology and mythology. The Jupiter star would be the second great celestial body after the Sun, and it would be worshipped, feared, and studied with the same intensity that ancient cultures directed at the Sun and Moon. For astronomers and scientists, the second star would be an object of supreme interest. Its spectrum, dominated by red and infrared, nearly devoid of blue, would be immediately recognizable as different from the Sun, and the science of stellar physics would be accelerated by having two stars in our own system to study directly. At interplanetary distances, with all the resolution that proximity allows, we could send spacecraft directly to Jupiter's star in decades to centuries, rather than the millennia required for even the nearest other stellar systems. We could study its corona, its flares, its magnetic activity, its stellar wind. We could directly observe the conditions around a red dwarf star, the most common type of star in the galaxy, in our own backyard. This would transform our understanding of stellar physics and the conditions for planetary habitability around red dwarfs, which is one of the most important and actively debated topics in current exoplanetary science. Red dwarf stars are of intense interest to astronomers searching for habitable planets because they are so numerous. More than 70% of all stars in the Milky Way are M-type red dwarfs, that if any fraction of them host habitable planets, they represent the majority of habitable real estate in the galaxy. Planets have been found in the habitable zones of red dwarfs, including Proxima Centauri b, around our nearest stellar neighbour, TRAPPIST-1's remarkable system of 7 Earth-sized planets, at least 3 of which may be habitable, and dozens of others. The habitable zones of red dwarfs are much closer to the star than Earth's distance from the Sun. Because red dwarfs are so dim, a planet must orbit very close to receive enough warmth for liquid water. This creates its own challenges: tidal locking, where the planet always keeps the same face toward its star, like the Moon facing Earth, and intense stellar flares. Since red dwarfs are magnetically active and frequently produce energetic flares that could strip planetary atmospheres or deliver lethal radiation doses to the surface. Whether red dwarfs can host habitable planets, and what conditions on such planets would be like, are questions that having Jupiter's star in our own system would help answer with unprecedented clarity. The existence of Jupiter's star would not just change Earth, it would change science, it would change culture, it would change the story we tell ourselves about the solar system and our place in it. It would give humanity a second star to study, to explore, to send missions to regard with awe on clear nights when it rises in the east, ruddy and unmistakable. A second sun that failed to be a sun but became something else, something its own. Something that transformed what it meant to live in this particular corner of the galaxy. Let us linger for a moment on what this would mean for the history of human thought about the cosmos, because it is among the most underappreciated consequences of the thought experiment. The entire edifice of human cosmology, the models of the universe, constructed by every civilization from ancient Mesopotamia to modern astrophysics, was built on the observation of a solar system with one star. The Ptolemaic model, the Copernican revolution, Newton's laws of gravity, Einstein's general relativity. Each of these was constructed by minds that lived in a one-star solar system, for whom the uniqueness of the sun was not a hypothesis, but an unexamined background substance. The entire concept of a planet, a body that orbits a star without itself being a star, was developed in a context where there was exactly one star to orbit. In a binary solar system, none of this would have been obvious. Ancient astronomers observing two luminous bodies in the sky, one overwhelmingly bright, one dim but clearly non-stellar in its behaviour, moving through the constellations on a known period, would have faced a much more complex interpretive challenge. Which object is the centre? Around which does the Earth orbit? What is the relationship between the two luminous bodies? The history of astronomy might have been accelerated in some ways. The evidence for a heliocentric system would have been somewhat stronger if there were two obvious luminous bodies at different distances, making the geometry of the inner solar system harder to confuse and made more complex in others, since understanding the mutual orbit of the two stars would require grasping gravitational dynamics at a level that Newton's successors barely achieved even with extensive mathematical tools. The development of stellar physics would have been transformed. In our history, the application of spectroscopy to stars, the decomposition of starlight into its spectrum of colours, revealing the chemical composition and physical conditions of stellar atmospheres, began in the 19th century with the work of Fraunhofer, Bunsen, Kirchhoff, and others, and led to the classification of stars by their spectra, the understanding of stellar evolution, and eventually the development of nuclear physics itself, since understanding the energy source of stars required nuclear physics, and the constraints on stellar structure provided powerful tests of nuclear theory. With Jupiter's star in the solar system, spectroscopy of a red dwarf star would have been possible as soon as spectroscopic techniques were developed, at a distance hundreds of times smaller than even the nearest other stellar system. The comparison between the Sun's spectrum and Jupiter's star spectrum, the difference between a 5,778 Kelvin G dwarf and a 2,500 Kelvin M dwarf, would have been immediately evident and immediately informative. The diversity of stellar types, which in our history was inferred from observations of distant stars, would have been directly observable in our own sky. The development of the concept of stellar habitable zones, the range of orbital distances from a star within which liquid water can exist on a planet's surface would also have proceeded differently. In our history, the concept of the habitable zone was developed in the context of a single star, and the habitable zones of other types of stars were extrapolated from first principles and from observations of the Sun. With a red dwarf in our own system, the contrast between the Sun's habitable zone 0.95 to 1.37 AU and Jupiter star's habitable zone, roughly 0.02 to 0.04 AU, much closer to the star due to its dimness, would have been directly observable and directly testable. If any of Jupiter star's original moons survived in that habitable zone, which they would not, given the destruction we described. But in the hypothetical scenario where they somehow did, they would represent prime targets for biosignature searches at interplanetary distances. The question of life around red dwarfs, which is one of the most pressing open questions in modern astrobiology, would have been answerable in our own solar system, rather than requiring telescopes capable of characterizing the atmospheres of planets orbiting distant stars. There is a specific observational question that Jupiter star would enable in our own solar system that would be of profound scientific value: the direct observation of stellar flares from a red dwarf at close range. Red dwarfs are magnetically active and frequently produce flares, explosive events in their atmospheres in which magnetic energy is rapidly released, heating plasma to tens of millions of Kelvin and emitting intense bursts of X-rays and extreme ultraviolet radiation. The flares from red dwarfs are of particular concern for the habitability of their closely orbiting planets, because the intense radiation of a major flare could strip atmospheric gases through photodissociation and thermal escape, and could deliver lethal radiation doses to the surface of any planet without a strong magnetic field or a thick atmosphere for shielding. Whether red dwarf flares represent a fundamental obstacle to the habitability of their planetary systems is an open question. With Jupiter star in our own solar system, we could study its flares directly, their frequency, intensity, spectrum, and effects on the solar wind and on the interplanetary medium in far greater detail than any observation of a distant stellar system could provide. We would have a living laboratory for the most common type of star in the galaxy, orbiting our own sun at a distance traversable by conventional spacecraft in decades rather than millennia. These are the scientific gifts that Jupiter star would have given us. The cultural gifts are harder to enumerate, but no less real. Every human culture has a sun mythology, a set of stories and rituals and beliefs organized around the central fact of the sun as the source of light, warmth, and life. In a binary solar system, every human culture would have had a second celestial deity, dimmer, redder, following a different path through the sky, rising and setting at different times from the sun, and carrying different connotations. In many ancient cosmologies, light and darkness are in opposition, and the sun is the champion of light against the forces of night and chaos. A second, dimmer, ruddier, ruggier light source in the sky would complicate this mythology in ways impossible to fully predict, but certain to produce a cosmology richer, stranger, and more varied than the one sun cosmology that all actual human civilizations have shared. The impact on mathematics and geometry would also have been real. The development of celestial mechanics, of the mathematical description of orbital motion, was driven in large part by the need to predict the positions of the planets. Newton's development of universal gravitation was motivated by the need to explain Kepler's laws of planetary motion, which described the elliptical orbits of the planets around the Sun. In a binary solar system, the three-body problem, the mathematical challenge of describing the motion of three gravitationally interacting objects would have been encountered immediately, rather than being a specialized mathematical curiosity. The three-body problem is, in general, not analytically solvable. There is no exact mathematical formula that gives the positions and velocities of three mutually gravitating bodies at all future times, unlike the two-body problem, which is exactly solvable. The French mathematician Henri Poincaré showed in the 1890s that the three-body problem is generically chaotic, sensitive to initial conditions, in a way that makes long-term prediction impossible. The discovery of chaos, which in our history was a product of late 19th and 20th century mathematics and physics, might have been forced on the attention of astronomers much earlier in a binary solar system, where the three-body problem was not a theoretical curiosity, but an everyday observational challenge. All of this is speculation, of course. We do not have a binary solar system. We have a single sun, a giant planet at 5.2 AU, and a biosphere that is evolved in the stable, predictable, single-star environment that this configuration provides. The speculation is instructive, precisely because it reveals how much of what we take for granted, the stability of Earth's seasons, the regularity of the day-night cycle, the single-source illumination that has shaped the evolution of our eyes and our circadian rhythms and our mythology, depends on the specific configuration of our solar system, and specifically on Jupiter being a planet rather than a star. And there is a final thought that the thought experiment opens onto, one that I think is the most important of all. Jupiter did not become a star. It became a planet, the largest planet, the dominant planet, the gravitational arbiter of the outer solar system, and in doing so, it became something arguably more interesting than a dim red dwarf would have been. A second red dwarf at Jupiter's distance would be, in the cosmic taxonomy, unremarkable. Red dwarfs are the most common type of star in the galaxy. Another one would be noted and studied, and ultimately understood within the framework of a well-developed astrophysical theory. But Jupiter is a planet, a world of storms and moons and magnetic fields and auroral displays and complex chemistry, a laboratory for every kind of planetary physics, operating simultaneously. A system in miniature with 4 major moons that are each full worlds in their own right is an object that continues to surprise us. Europa may have a subsurface ocean with more liquid water than all of Earth's oceans combined, heated by tidal flexing from Jupiter's gravity, protected from Jupiter's intense radiation by an ice shell kilometers thick. Io is the most volcanically active body in the solar system, its surface continuously resurfaced by sulfurous eruptions driven by tidal heating. Ganymede is larger than Mercury and has its own magnetic field. Callisto's ancient cratered surface preserves a record of the early solar system that no other body has maintained. These moons exist because Jupiter is a planet. If Jupiter were a star, the massive radiation and stellar winds would have stripped the inner moons of any volatile chemistry, would have baked the icy satellites into bare rock, would have created a miniature stellar system rather than the extraordinary collection of planetary worlds that we can visit with spacecraft, that we have already sent 4 separate spacecraft to explore up close. The Galileo mission orbited Jupiter for 8 years and transformed our understanding of the Jovian system. The Juno mission is mapping Jupiter's interior structure and magnetic field with unprecedented precision. The Europa Clipper, launched in 2024, is on its way to study Europa's ocean from close orbit, seeking to determine whether the conditions for life exist beneath that ice shell. These missions exist because Jupiter is a planet, a world with surfaces and oceans and atmospheres and geology. A world where chemistry happens and complexity accumulates, and the conditions for something extraordinary might, just might, be present. Jupiter failed to be a star. And in that failure, it became something the galaxy produces far less commonly than stars: a system of worlds, a collection of potential homes, a laboratory for planetary science, a gravitational shepherd of an inner solar system, where, on one small rocky planet, chemistry managed to become biology, and biology managed to become consciousness, and consciousness managed to build telescopes and point them at Jupiter and wonder, with genuine curiosity and not a little vertigo, what would have happened if things had gone differently. The universe did not owe us a planet Jupiter. It could have given us a star instead. The fact that it gave us a planet, that the mass distribution in our protoplanetary disk, the timing of the sun's ignition, the location of the snow line, the accidents of accretion, conspired to produce a planet rather than a star in that particular orbit, is not something we should take for granted. It is not something we should view as inevitable. It is a contingency, a roll of the cosmic dice that came up planet rather than star, and in doing so gave us not just the largest planet in the solar system, but a shield, a shepherd, a wonder, and possibly, if we are right about Europa's ocean, a world that harbours life in the very object whose transformation into a star would have threatened ours. Consider the full arc of what Jupiter's existence as a planet has meant for the history of this solar system. Jupiter's gravity sculpted the asteroid belt, preventing a planet from forming between Mars and Jupiter, keeping the belt in its current configuration of millions of rocky and metallic bodies in stable orbits. Jupiter's orbital migration, early in the solar system's history, the Grand Tack, shaped the inner solar system, reducing the mass available to form Mars, scattering the primordial disk, and enabling the delivery of water and carbon to the inner solar system from beyond the snow line. It was Jupiter's gravitational influence that flung the comets and asteroids, that brought water to the early Earth, the water that fills the oceans, the water that is the medium of all terrestrial biochemistry, the water without which life on Earth would never have begun. And it is Jupiter's gravity that continues today to deflect some fraction of comets and asteroids away from the inner solar system, reducing the frequency of the largest impacts that could threaten complex life on Earth. Jupiter did not do any of this intentionally. It is a ball of gas. It has no intentions. It executes Newton's laws of gravity with perfect fidelity and with complete indifference to what results. But the results, across 4.6 billion years of gravitational interaction, have been this solar system, this specific arrangement of worlds in which Earth happens to be habitable, in which the bombardment rate has been high enough to deliver water and organics, but low enough to allow the continuous evolution of complexity, in which the giant planet in the outer system has served as both sculptor and shepherd of the inner worlds. This is not necessarily the only path to a habitable inner planet. Many solar systems without Jupiter equivalents may also produce habitable planets. But it is our path. It is the path that led to us. The thought experiment of what if Jupiter became a star is, at its heart, a thought experiment about contingency, about the fact that the universe contains enormous possibility space, that the same raw materials, hydrogen, helium, hive elements seeded by previous generations of stars, can assemble into wildly different configurations depending on the initial conditions and the stochastic accidents of early evolution. In some configurations, the solar system forms with 2 stars, in some with no giant planets, in some with giant planets in the inner system rather than the outer, in some with a giant planet that migrated all the way to the inner system and destroyed all the terrestrial planets before settling into a close orbit around the star, the so-called hot Jupiters. Discovered by the hundreds by the Kepler mission, which appear to be giant planets that migrated inward and whose presence would have eliminated any inner rocky planets in the process. Our solar system is one outcome of a vast distribution of possible outcomes, and we inhabit it because we can, because it turned out, through contingency and chance, and the specific initial conditions of our solar nebula, to be the kind of system in which beings capable of asking these questions could arise. That is not a scientific conclusion. It is a philosophical one. But it is one that the science makes possible. The science of planetary formation, of solar system dynamics, of stellar physics, of astrobiology. And it is one that would not be available to a civilization living in a binary solar system, who would be asking a different question entirely. What if that second star had never formed? What would our solar system have looked like with only one sun? The universe, in giving us Jupiter as a planet rather than a star, gave us something more valuable than a second sun. It gave us a neighbour. And neighbours, as it turns out, are harder to come by and more worth keeping than stars.